The universe sits on a knife's edge. If gravity were stronger, even a fraction, or if the energy of empty space were just a little bit greater, everything would cease to exist. The stars, the atoms in your hand, all of it. That's the mystery of cosmic fine-tuning. It forces a staggering possibility. Our cosmos, with all its life, might not be a solitary accident. It could be one rare page in an infinite cosmic library. The multiverse. There are specific, razor-thin constants that allow us to exist. They point to realities beyond our own. The slightest change to the laws of physics would erase our reality. So we have to explore whether a hidden multitude of universes is the only answer. What does it mean to live in a universe that seems perfectly designed for life? The universe is like a clock, a cosmic clock, and for it to work, for galaxies to form, for atoms to come together, all its internal settings had to be exactly right. These are the constants, fixed numbers in reality: the speed of light, the strength of gravity, the force that holds nuclei together, the mass of an electron. We don't derive these numbers, we just measure them, we write them down, and they seem arbitrary. They could have been anything. But if any one of them was even slightly off, the clock would never have ticked. If gravity was stronger, stars would burn out in millions of years. No time for planets, no time for life. If the nuclear force was weaker, hydrogen wouldn't fuse. There would be no stars, just a dark, cold fog. It's like a watchmaker built a timepiece where every gear, every spring is precisely the right size. Not by accident, by design. The slightest flaw and the hands don't move. This leads to an idea, the Anthropic Principle. It says the universe we see must allow for observers. We're here, so of course the constants permit it. It sounds circular, but it opens a deeper question. Why, out of infinite possible settings, why this one? This life-permitting combination, the improbability is staggering. It's like finding one perfect watch in a desert. A desert that goes on forever, filled with broken gears and silent metal. So we have this knowledge, we've measured the clock, we know it's perfect, and now we have to ask who set the time. Gravity is the thing that holds the universe together. It's the first line on the blueprint. But if that line were just a little darker, if gravity were stronger even by a fraction, the whole story would be short. Stars would burn with a ferocious intensity. They'd use up their fuel not in billions of years, but in millions. They'd flare up, brilliant and brief, and then collapse into darkness. There'd be no time for planets to cool, no time for complex chemistry, no time for life to even begin. The stage would be set and then immediately torn down. If gravity were weaker, you get the opposite problem. Matter would struggle to clump together. The great clouds of gas that birth stars might never coalesce. Galaxies might never form. The cosmos would just be a thin, dark, lonely soup. The gravitational constant isn't a round number. It's a precise, seemingly arbitrary value. And it sits perfectly between two catastrophes. Physicists like Sir Martin Rees have pointed to this balance. It's a profound hint of fine-tuning. It's as if the universe's expansion and the pull of matter were set as a perfect counterweight from the very beginning. This isn't about making life comfortable. It's about making life possible at all. So you look at this first constant, this fundamental force, and you see a universe that had to be built this way for us to be here. The improbability is immense. Was it luck? A single, perfect roll of the dice? Or does this precise setting point to something else? A deeper architecture, where every possible value of gravity plays out somewhere. To find out, you have to look at the next constant, the very glue that holds reality together. That perfect counterweight is just the start. There's another constant, even more mysterious, and its balance is even more delicate. It's the energy of empty space, the cosmological constant, sometimes called dark energy. It's not really a thing, more a property of nothing. A gentle push, built into the vacuum itself, that makes the universe expand faster and faster. And the value of this push is incredibly small, unbelievably small. But if it were just a little stronger, the whole story would have ended before it started. The expansion would have been too violent, too fast. Matter could never have clumped together, not into stars, not into galaxies. Every particle would have been ripped away from every other particle. A catastrophic event, the Big Rip. The universe tearing itself apart in a flash, leaving nothing but a cold, empty, accelerating void. But if the push were just a little weaker, the opposite happens. Gravity wins. After the Big Bang, the expansion slows, stops, and then reverses. Everything, all matter, all energy, comes crashing back together, a fiery collapse. The Big Crunch. The universe becomes a brief, hot, self-destructive event. And the value we actually measure sits right between them, perfectly, impossibly. Between those two catastrophes, it's like walking a tightrope over an immense abyss. One tiny lean in either direction and you fall. The physicist Steven Weinberg, he calculated how fine this balance is. He found the cosmological constant is tuned to about 1 part in 10 to the 120th power. That's a 1 with 120 zeros after it. A number so small, so precise it seems chosen. It can't be explained by any physics we know, it just is, and its existence in this exact amount gave the universe the room to build galaxies. Stars, planets, us. This isn't just another puzzle piece, it's a cornerstone, a razor's edge balance that points to a reality where our existence isn't just lucky. It feels orchestrated by the deepest rules of everything. Fine-tuning isn't just about gravity or the expansion of the universe. It goes deeper into the particles themselves. Take the proton and the electron. The proton is heavy, it's the anchor in the center of the atom. The electron is light, it moves fast around it. Their masses are completely different. A proton is about 1/836 times heavier than an electron. That number is a fixed constant. It looks like a random fact from a textbook, but it's fundamental. If that mass ratio were even slightly off, the universe would be sterile, chemically sterile, because that dance between the proton and the electron, that's what makes chemical bonds. Water, oxygen, the chains of DNA, all of it depends on this balance. If the electron were heavier, it would be sluggish. It wouldn't orbit right. The attractions between atoms would fail. Molecules couldn't form. If the proton were lighter, the nucleus would be unstable. Atoms would fly apart. You'd get a universe that never gets past hydrogen. Just a cold sea of single atoms, nothing linking together. No water, no carbon, no complex chemistry. Quantum chemists say for organic molecules to emerge, these particle masses had to be in a razor-thin window. The specificity is breathtaking. This isn't about making life easy. It's about placing the very first stone, the correct stone, so the whole cathedral of complexity could be built later. So now we have 3 precise settings: the strength of gravity, the energy of empty space, and the mass ratio of the particles that build everything. Each one tuned to avoid a different cosmic dead end. Each one essential. The odds of all these aligning by pure chance in one universe are vanishingly small. It feels less like a random roll of the dice and more like opening a combination lock. But if it wasn't chance, and it wasn't design in the traditional sense, then what else could explain it? The answer might be in a concept so vast it redefines reality itself. That staggering improbability, that's really the heart of it. It's not just that the universe is finely tuned. It's how finely tuned. Scientists try to put a number on that. They take each constant, like gravity's strength or the energy of empty space, and they calculate its life-permitting window. How much could this number wiggle before everything falls apart? And the answer is always the same: almost not at all. For the cosmological constant, that window is unimaginably tiny. You could change it by only 1 part in 10 to the 120th power. That's a decimal point, then 119 zeros, and then a 1. A number so small it just defies comprehension. It's not a narrow window. It's a pinhole in a sheet of steel viewed from miles away, and that's just one constant. The mass of the electron, the strength of the nuclear force, the initial smoothness of the Big Bang, each one has its own, equally minuscule, life-permitting range. When you combine these probabilities, you're not just multiplying small numbers. You create a number so close to zero it might as well be impossible. Imagine winning the biggest lottery on Earth. Now imagine winning it again, every single second, for the entire age of the universe. The odds of our universe's specific settings emerging by pure, random chance are even smaller than that. So this presents a profound dilemma, a choice between two staggering ideas. The first is that we are the beneficiaries of the most monumental, singular stroke of luck in all of existence. That against all conceivable odds, every dial on the cosmic control panel just happened to land in the perfect position. The second idea is that there must be another explanation. That this apparent miracle isn't a miracle at all, but a consequence of a deeper, broader reality. And this is where the improbability argument becomes an engine. It pushes us toward the multiverse, because if there are an infinite number of universes, each with different random settings, then a universe like ours isn't a statistical miracle. It's a statistical inevitability. Somewhere in that vast ensemble, a universe with the right numbers had to appear. We just happened to be in it. The cosmic lottery wasn't won once. It's being played with every possible combination, an infinite number of times. This is the puddle argument. You have a puddle of water in a hole, and the puddle looks around and thinks, "This hole fits me perfectly. The shape of it matches my own shape exactly. It seems like an incredible coincidence, like it was designed for me." But of course, the hole wasn't made for the puddle. The puddle just filled the space that was there. That's the weak Anthropic Principle. We see a universe with these specific constants because we're here to see them. If the constants were different, we wouldn't be here to notice. It's a selection effect. It feels circular. It feels like a tautology, and it is in a way. But it's an important circle. It means we can't observe a universe that doesn't allow us to exist. That's a filter on everything we see, but it's unsatisfying. It explains why we see a life-permitting universe, but not why a life-permitting universe exists to begin with. The puddle analogy breaks down because the hole was already there. For our universe, the question is why the hole, the laws of physics, has this particular, life-allowing shape at all. That's where the strong Anthropic Principle comes in. It goes further. It suggests the universe must, in some sense, have properties that allow observers to arise. It's not just that we see what we can see. It's that the universe is compelled toward producing life, toward producing consciousness. This shifts from a statement about observation to a statement about the laws themselves. It hints at a deeper link between consciousness and the cosmos. But does that solve it? Or does it just push the mystery back one step? Saying the universe must allow life doesn't explain the mechanism. It doesn't tell us how or why the constants landed on these razor's edge values. It feels less like an answer and more like a philosophical stance, a declaration. The debate is fundamental. Is fine-tuning a puzzle that needs a causal explanation? Or is it just a brute fact, a starting point with no deeper reason? The Anthropic Principle, in both forms, forces us to confront our own place in the question. We are not neutral observers. We are products of the very thing we're trying to explain. That self-referential loop is where physics meets philosophy. It suggests maybe the answer isn't found by looking harder at our single universe, but by stepping outside of it, to a framework where all possible holes exist, all possible sets of constants, a place where the puddle's amazement isn't a logical error, but a simple truth of its particular location in a much vaster landscape. That self-referential loop it pushes toward a radical answer. The multiverse, that's the idea that could break the cycle. And this isn't just science fiction anymore. It's a serious framework. In some circles, it's the leading one. It comes out of our best theories of the cosmos. Take inflationary cosmology, the leading model for the Big Bang. It suggests our entire observable universe is just one patch, one bubble, in a much vaster, eternally expanding sea of space-time. And in that eternal expansion, new bubbles are constantly forming. Each one is a separate universe with its own Big Bang. These bubbles can have different properties, different fundamental constants, different laws of physics. It's like a cosmic foam where every bubble is an entire reality. String theory points the same way. It's an attempt to unify all forces, and it proposes a landscape of possibilities. A staggering number of stable configurations for the extra dimensions it requires. Each configuration could be a different universe, with a different set of physical laws. So the multiverse isn't a wild guess, it's a prediction. It falls out of our most ambitious attempts to understand reality. Picture it, an almost infinite ensemble of universes. A cosmic library where every possible book of physics is written. In most of those books, the story is short and bleak. The constants are wrong. Gravity crushes everything instantly. Or atoms never form, or the universe rips itself apart in a flash. These are dead universes, silent and empty, but in a very, very few volumes by sheer chance all the numbers line up. The constants fall into that razor-thin window, the life-permitting one. In those rare universes, galaxies can form, stars can shine, and on at least one rocky planet, creatures can arise. Creatures that wonder about it all, that's us. We are in one of those rare books. This reframes everything. Our universe's improbable fine-tuning, it stops being a miracle. It becomes a statistical inevitability. If you roll the dice an infinite number of times, every possible combination comes up, no matter how unlikely. We are just the result of that one lucky roll. The multiverse offers a purely naturalistic explanation. There's no need for a single, special tuning event. No need for a designer. Just the relentless, blind generation of possibilities. Across a reality so vast it defies comprehension. Our existence isn't a central event. It's a local accident, in one corner of a hidden multitude. So, the question is where this library comes from. How you get all these different sets of rules. The main scientific answer points to a moment right after the Big Bang, to a theory called cosmic inflation. The idea is that the beginning wasn't smooth. It was a sudden, explosive stretch. Space itself expanded unbelievably fast in a tiny fraction of a second. It grew by a factor of trillions, and this wasn't things moving through space. This was space itself getting bigger. And the models from people like Guth suggest this process didn't just happen once. In a version called eternal inflation, it never really stops. You can think of it like water boiling. Bubbles form in the water. In this case, the roiling medium is the inflating field of space-time, and the bubbles are spots where inflation randomly stops. When it stops inside one of those bubbles, the energy driving the expansion is released. It turns into a hot, dense soup, a Big Bang. That bubble becomes a universe with its own laws, depending on how that inflation field settled. But outside that bubble, the inflation keeps going. It continues forever. New bubbles keep forming in that inflating background, an infinite number of them. Each one is a separate pocket universe, cut off from the others. They're like islands, and the key is how the field settles inside each bubble. Physicists call it the field finding its lowest energy state. It can happen in different ways. It's like a ball rolling down a landscape with lots of hills and valleys. Depending on where it starts, it can end up in different valleys. Each valley is a different stable setup for physics, a different set of constants. So in one bubble universe, the ball rolls into a valley that gives you a certain strong nuclear force. In another, it gives you a different gravity. Most of these valleys produce dead universes, universes that collapse right away or where no atoms form. But because of the sheer numbers in eternal inflation, a few bubbles will, by pure chance, land in the right valley. The one valley out of countless ones, where all the numbers line up to allow stars and planets and life. This isn't a fringe idea. Eternal inflation is a direct extension of the inflationary theory that explains our universe, its smoothness, its flat geometry. It gives you a physics-based mechanism for creating a multiverse. It suggests fine-tuning might not need an explanation from outside physics. It could just be the outcome of a process that generates every possible physics, everywhere. We just happen to be in one of the rare bubbles where the numbers worked. A single bubble of habitability in an infinite cosmic ocean. Eternal inflation gives us the bubbles. But then, what sets the rules inside each one? What decides the constants? This is where physics reaches for its most ambitious idea, a theory of everything. That's string theory. It says the fundamental building blocks aren't point-like particles. They're tiny, vibrating strings. Different vibrations make different particles. An electron is one note. A quark is another. It's an elegant idea that could unify all forces, but it comes with a consequence, a profound one. For the math to work, string theory needs extra dimensions of space. Not just the 3 we know, but maybe 6 or 7 more, curled up incredibly small, and here's the key. There isn't just one way for these extra dimensions to curl up. They can fold and twist into a staggering number of stable shapes. Each shape creates a different, self-consistent set of physical laws, a different vacuum state. Think of it like a cosmic instrument with an almost infinite number of tuning pegs. Each adjustment of the pegs gives you a different song, a different universe. Physicists call this the landscape, the string theory landscape, and its size is almost incomprehensible. The number of possible stable configurations, each a potential universe, might be around 10 to the 500th power. That's a 1 with 500 zeros after it. A number so vast it dwarfs the number of atoms in our observable universe, so the landscape provides the menu. And eternal inflation, the boiling process, is the chef. It randomly samples from this menu, creating bubble universes with every possible set of laws. In this picture, our universe is just one specific tuning, one particular song that came out of the chaos. The cosmic dice here has 10 to the 500 faces. And almost all of those faces are silent, dead universes. Universes that collapse instantly, or where matter is unstable, or where forces are too weak to build anything. But with that many roles happening across an eternally inflating multiverse, it becomes statistically inevitable that a few faces land on a life-permitting combination. Ours is one of them. We are not a special creation. We are a statistical fluctuation, a rare but inevitable outcome in a cosmos of limitless variety. This connection is crucial. It shows how the mystery of fine-tuning doesn't just point toward the multiverse. It actively shapes our search for the deepest laws. The string theory landscape offers a potential answer to the why. It gives a framework where all possible physics exist, so ours isn't a puzzle to be solved, but a location to be mapped. Yet, for all its mathematical beauty, this is a profound challenge. The string theory landscape and the multiverse it implies is currently untestable. We can't see beyond our bubble. We can't probe those other configurations. It lives in the realm of prediction, not proof, so we're left at this frontier, holding a theory that explains everything in principle, but confirms nothing in practice. The fine-tuning of our universe points to a hidden multitude, and our best fundamental physics sketches its blueprint. But the blueprint is for a castle we may never enter. But that cosmic bubble landscape isn't the only picture of a multiverse. There's another one, and it doesn't come from cosmology. It comes from the rules of the very small, quantum mechanics. At the center of quantum theory there's this puzzle. A particle, an electron, it doesn't have a definite location until you measure it. It's in a haze of possibilities, a superposition, it's everywhere it could be, all at once. Then you observe it, you take a measurement, and that seems to force it to pick one state. One definite spot. But why? What is actually happening during that collapse? There's an answer from Hugh Everett back in the 1950s, a radical one. It says nothing collapses. Instead, every possible outcome of a quantum event, it actually happens. but it happens in a new, branched-off reality. That's the many worlds interpretation. You can think of it like a story. Every choice a character makes splits the narrative. In one branch, they go left. In another, they go right. Both stories are real. They just play out on parallel pages. And in the quantum world, this happens constantly, for every particle, every interaction. Anytime an electron could go here or there, the universe splits. One world has the electron here. Another world, identical in every other way, has it there. This branching isn't a metaphor, it's the mathematical heart of the theory. The wave function, which describes all the possibilities, it never collapses. It just keeps evolving. And we, as conscious observers, we get entangled with one specific branch. We follow one thread of the story. We never see the others splitting away. Now, these parallel worlds from quantum branching, they're different from the bubble universes. In the many worlds picture, the branches usually share the same laws, the same physics. What's different are the historical events, the outcomes of chance. In one world, a radioactive atom decayed a second earlier. In another, you made a different choice this morning. The fabric of reality is woven from an infinite number of those threads. Thematically, though, it points the same way as the cosmological multiverse. It suggests a deep pluralism. Reality isn't a single straight line, it's a sprawling tree. Always diverging, where inflationary cosmology gives us a spatial multiverse. Different physics in different places, the many worlds interpretation gives us a temporal multiverse. Different histories, both ideas coming from totally different parts of physics, they converge on one suggestion. Our classical intuition that there's one objective reality we all share, it's an illusion. A limited view. We're not at the center of a solitary cosmos. We're walking one path in a forest of realities, so dense, so vast that every possibility is realized somewhere. This quantum view adds a personal dimension to the multiverse. It means for every moment of uncertainty in your life, every crossroads, there's another version of you living the path you didn't take. It stretches what it means to be an individual, what it means for a universe to be real. It tells us the hidden structure of everything might be far more expansive, more interconnected, more prolific than our everyday minds can grasp. The multiverse has a lot of explanatory power, but it also faces serious criticism. The most common objection is pretty stark. If we can never see these other universes or interact with them, is it even science? Science is about testable predictions. A theory should forecast what we observe, and some argue the multiverse doesn't do that. It can't be falsified, it can't be proven wrong. In a way, it explains too much. By saying every possible universe exists, it can account for any observation. Our universe allows life, of course it does, somewhere in the multiverse. To critics like the philosopher Karl Popper, that makes it not a scientific theory. It's a metaphysical speculation, a theory of anything that, in practice, predicts nothing. It becomes an untouchable idea, insulated from evidence. This isn't just academic. It strikes at how we seek knowledge. Are we exploring reality or telling a just-so story? A narrative that makes us feel better about our improbable existence, but one that lies forever beyond experiment. Then there's a more bizarre logical puzzle. It's called the problem of Boltzmann brains, named for the physicist Ludwig Boltzmann. It comes from the idea of an eternal, infinite multiverse. In that kind of cosmos, random fluctuations can create anything. Given enough time and space, particles jostling by accident could assemble a fully formed, conscious brain. A disembodied observer with false memories of a past that never happened. In an infinite multiverse, these random fluctuations should happen. So the question is, which is more likely? That a complex, ordered universe like ours evolved over billions of years to produce beings like us? Or that a single, conscious brain just popped into existence from chaos, with the illusion of that entire history? The math is counterintuitive. In an infinite sea of disorder, isolated pockets of order. Like a single brain, are actually more probable than vast, sustained islands of order. Like our entire cosmic history, so if the multiverse is real and infinite, then Boltzmann brains should vastly outnumber evolved beings like us. Statistically, we should be Boltzmann brains. But we have overwhelming evidence of a consistent, lawful past. Fossils, cosmic microwave background radiation, the layered history of stars that creates a paradox. Our observations tell us we are evolved beings in an old universe, but the multiverse, taken to its logical extreme, suggests we are far more likely to be momentary illusions. This is a serious challenge. It suggests the multiverse may contain the seeds of its own absurdity, predicting that most observers should not see a world like ours at all. Philosophers of science raise another issue, more fundamental. Does the multiverse actually solve the fine-tuning problem, or does it just relocate it? Imagine walking into a vast, endless warehouse, filled with clocks, millions of them, all broken, gears scattered. But in one corner you find a single, perfectly functioning clock. You might say, of course there's a working clock here. With so many attempts, one had to work by chance. But that doesn't explain why the warehouse exists in the first place, or why it contains the parts that could, even rarely, assemble into a functioning clock. The multiverse, critics argue, is that warehouse. It may explain why a life-permitting universe exists because every possible one exists. But it does not explain why the multiverse itself has the capacity to produce such a universe. Why is the landscape of string theory so vast? And why does it contain even one stable configuration that permits life? Why do the laws underlying eternal inflation allow for such a fertile process? The fine-tuning problem may just be pushed back one step. Instead of asking why our universe's constants are just right, we now must ask why the multiverse's laws are such that a universe like ours is even possible. The mystery remains. It's just been moved to a grander, more hidden stage. Engaging with these objections isn't about dismissing the multiverse. It's about honest exploration. It reminds us that the most profound ideas in science live at the edge of what we can know. They challenge our methods and our logic, and our very understanding of what an explanation should be. These objections show the multiverse isn't a simple answer. It's a debated frontier, and because fine-tuning is such a deep question, other explanations have come from outside physics. They offer a different kind of answer. One appeals to purpose, the other to technology. The first is intelligent design. It looks at those razor's edge constants and sees not chance, but intention. It posits a cosmic designer, a mind that set the dials to allow life. This idea resonates because it fits a human pattern. When we see something intricate and purposeful, like a watch, we infer a watchmaker. The universe, in its precision, seems to demand that. It's a philosophical stance. It finds meaning in the tuning itself. It reads the improbability as evidence of a plan. The second is the simulation hypothesis. It suggests our universe isn't fundamental but constructed, a sophisticated reality made by an advanced civilization. Maybe as an experiment or art or computation. Here, the constants are parameters in a program. They are tuned because the programmer chose them. This idea has gained traction now, as we create simulated worlds ourselves. It reframes the mystery. It's not about cosmic origin anymore, but about technological hierarchy. Are we the base reality, or are we someone else's simulation? It's crucial to understand these aren't scientific theories like the multiverse. They operate on different ground. Intelligent design and the simulation hypothesis are philosophical responses. They offer narratives. They provide a kind of closure, an answer to the why that feels satisfying. But they do it by introducing new things, a designer, a simulator, that are themselves unexplained and untestable. The scientific method, by contrast, looks for explanations within natural law, and it demands testable predictions. That's the key distinction. The multiverse, for all its strangeness, comes from within our best scientific frameworks. It's a prediction of inflationary cosmology and string theory. It offers a naturalistic mechanism, eternal inflation sampling a vast landscape, that could, in principle, be tested. We might find signatures in the cosmic background radiation, or derive predictions that only make sense in a multiverse. The search is active even if the evidence isn't here yet. The other ideas, while significant, don't offer a path to falsification. They answer a mystery with a deeper mystery. That doesn't make them wrong. It puts them in a different category. They highlight a deep human desire to find meaning or agency or familiarity in the cosmic precision. We look for the watchmaker, or we recognize our own potential to become creators. Ultimately, these alternatives show the weight of the original question. The fine-tuning of the cosmos isn't a minor puzzle. It's a profound anomaly. It pushes at the limits of science, philosophy, and human understanding. It forces us to consider possibilities that once seemed like fantasy. And in doing that, it reveals something. Not just the potential structure of reality, but the nature of our quest to comprehend it. We are drawn to the edges, looking for a story that makes sense of the numbers. Whether that story is infinite bubbles, a guiding intelligence, or lines of code in a vast computer. The search itself tells us something. We are here in this improbable universe, compelled to ask why. The fine-tuning of the cosmos is why we're here to think about it. Those razor-thin constants built a stable universe, but they also wrote the recipe for life. It starts in the hearts of stars. That's where the universe forges the elements. Stellar nucleosynthesis. It's this nuclear alchemy that turns simple hydrogen and helium into everything else. The carbon in your cells, the oxygen you breathe, the iron in your blood. All of it was forged in stellar furnaces, then scattered by dying stars. But this cosmic chemistry needs a perfect balance. The strength of the nuclear forces has to be exactly right. If the strong nuclear force, the one that binds atomic nuclei, was just a few % stronger or weaker, the whole chain of creation breaks. And it breaks at carbon. Carbon is the backbone of biology. It's the versatile element that forms long chains, complex rings, the foundation of proteins, DNA, every organic molecule. For life as we know it, carbon is non-negotiable. But making carbon in stars is a two-step dance of incredible precision. First, helium nuclei fuse to make beryllium-8. But beryllium-8 is wildly unstable. It falls apart in a fraction of a second. For carbon to form, a third helium nucleus has to strike that beryllium-8 nucleus in the fleeting instant before it decays. The odds seemed impossibly low, like trying to build a house of cards in a windstorm. The physicist Fred Hoyle looked at this in the 1950s. He reasoned that for our carbon-rich world to exist, there had to be a helping hand within physics itself. He made a prediction. He calculated that inside stars, the carbon nucleus must have a very specific, resonant energy level. A kind of nuclear welcome mat. Something that would dramatically increase the chance of that third helium nucleus sticking. This resonance would act like a catcher's mitt, perfectly tuned to grab the pieces and assemble carbon. At the time, no such energy level was known. Hoyle went to nuclear experimentalists and told them where to look. They were skeptical, but they looked. And they found it, exactly where Hoyle predicted. It's now called the Hoyle resonance, a precise, seemingly arranged feature of nuclear physics. Without it, the production of carbon in stars would be negligible. The universe would be hydrogen, helium, a little bit of other light elements, but no carbon, no chemistry of life, no planets like Earth, no us. This is where fine-tuning moves from cosmic architecture to personal biography. That specific nuclear resonance isn't a universal necessity. It's a specific setting on the dial, a setting that lets stars become factories for the building blocks of biology. It connects the force that holds atomic nuclei together directly to forests, oceans, conscious minds. The oxygen we breathe was forged in similar, finely tuned reactions. So was the nitrogen in our atmosphere, the phosphorus in our DNA. The universe didn't just create a safe stage. It populated that stage with the exact materials needed for the play of life to begin. When we trace our biological lineage back, we don't stop at the first single-celled organism, we go further, back to the supernova that enriched the galactic cloud, back to the main sequence stars that cooked the elements, back to the fundamental constants that made those stellar kitchens possible. Our story is written in stellar ash, assembled by laws of breathtaking specificity. This link from nuclear physics to biology makes the fine-tuning argument intimate. It suggests we aren't just accidental inhabitants of a habitable zone. We are a blossoming of the cosmos itself, a consequence of its deepest, most precise settings. The multiverse idea finds traction here. In a landscape of infinite possible physics, most universes would lack the Hoyle resonance. They'd be stillborn, chemically inert. We find ourselves in one of the rare branches where the nuclear music plays the right notes to build composers. The chemistry gave us the building blocks, but it didn't build the house. For that, you needed architects, on a cosmic scale, and that brings us to the most dominant parts of the universe. The parts we can't see. Dark matter and dark energy. Together they make up about 95% of everything, and their specific natures. That's another layer of precise calibration. First, dark matter, we can't see it. It doesn't emit light, doesn't absorb it, but we know it's there because of its gravitational pull. It's the hidden scaffolding. After the Big Bang, ordinary matter, the stuff for stars and planets, was spread too thin, moving too fast. It couldn't clump together under its own gravity. Dark matter provided the extra grip. Its invisible halos acted as seeds. They gathered the hydrogen and helium gas. Only then could galaxies begin to form. The amount of dark matter, its specific properties, had to be just right. If there were too much, or if it were too sticky, the universe would have overclumped. Galaxies would have formed too early, too dense. They would have collided and merged violently, disrupting the orderly orbits of stars. Planetary systems would be rare. Unstable. If there were too little dark matter, the opposite happens. Gravity wouldn't have been strong enough, not against the universe's rapid initial expansion. The cosmic gas would have remained a diffuse haze, thin, no galaxies, no stars, just a lonely, dark emptiness. The amount we observe is a perfect middle ground. It allowed for grand, spiral galaxies, like our Milky Way, galaxies with quiet suburbs, where solar systems can form and persist for billions of years. In relative peace, then there is dark energy. This is the mysterious force causing the expansion to accelerate. We see its effect in distant galaxies. It behaves like a repulsive force, woven into the fabric of space itself, and its value is impossibly small, yet critically non-zero. Its role in fine-tuning is about timing. Dark energy acts as a cosmic throttle. In the early universe, it was negligible, that allowed dark matter to do its work, building the large-scale structure. But as the universe expanded, as matter thinned out, dark energy's gentle push began to dominate. This is happening now. If dark energy had become dominant too early, it would have shut down galaxy formation before it really got started. The cosmic construction project would have been abandoned. If it were stronger, it would have ripped apart galaxies, even atoms, in a catastrophic big rip. If it were weaker or negative, gravity would have eventually won, leading to a big crunch, a universe that collapses back on itself, that offers no long-term future for life. So you have this balance. Dark matter provides the structure. Dark energy provides the space. One pulls things together to build islands of complexity. The other ensures those islands aren't destroyed too soon, or crowded into chaos. Their precise contributions create a universe that is both richly structured and long-lived. Astonishingly long-lived. Enough time for stars to live and die, forging heavy elements, enough time for planets to cool, for chemistry to become biology. Enough time for intelligence to evolve, and to look back at the cosmos, wondering how it all came to be. We still don't know what dark matter and dark energy fundamentally are. They are two of the greatest mysteries in physics, but their effects are measurable, and those measurements reveal another set of numbers that had to fall within a narrow range. This isn't just about the strength of forces anymore, or the mass of particles. It's about the very skeleton of the cosmos and its breadth. The fact that these two unknown entities exist in just the right proportions. To craft a habitable universe, it feels like more than coincidence. It feels like part of a pattern of calibration so deep it touches every scale. From the quantum to the cosmic, this calibration pattern, it's not a new idea. People have felt the cosmos has a deep order for a long time. For centuries, the universe was seen as this magnificent clock. Isaac Newton's laws described a world of perfect predictability. Planets moved in their orbits with mathematical certainty, a grand mechanical system, governed by fixed universal principles. To Newton, and to many after him, that clockwork precision pointed to a divine clockmaker, an intelligence that set the gears in motion. The laws themselves were seen as elegant, beautiful, even sacred, but they weren't questioned. They were the starting point, the given rules of reality. That view started to shift in the early 20th century, with Albert Einstein. His theory of general relativity replaced Newton's force of gravity with the curvature of space-time itself. A more profound set of equations, more beautiful, but Einstein ran into a problem. His equations predicted a universe that was either expanding or contracting. The static, eternal cosmos he believed in was unstable. To fix it, he introduced a fudge factor, a cosmological constant, a repulsive force to balance gravity and keep the universe still. He later called that his greatest blunder, because soon after, Edwin Hubble observed that distant galaxies were all rushing away from us. The universe wasn't static. It was expanding. Einstein's original equations without the constant had been right all along. That was a pivotal moment. It showed the laws of physics could contain hidden, specific predictions about the universe's behavior. Predictions you could confirm or refute by observation. Other scientists around that time began to notice something else. The numbers. The physicist Arthur Eddington was fascinated by the dimensionless constants of nature. Pure numbers, like the ratio of the electromagnetic force to the gravitational force between a proton and an electron. That number is enormous, around 10 to the 39th power. Eddington wondered why it had that specific value. He sensed it was a clue to a deeper truth. He and others started to wonder if these numbers weren't arbitrary but necessary. The output of some grander, unified theory. That was the seed of the modern fine-tuning problem. As 20th century cosmology advanced, it didn't just reveal a universe governed by laws. It revealed a universe governed by laws with very specific, very peculiar numerical values. Values that seemed oddly suited to the emergence of complexity. Einstein himself, even though he resisted quantum mechanics, expressed a kind of awe. He famously said the most incomprehensible thing about the universe is that it is comprehensible. That our minds can decode its mathematics. That hinted at a mysterious congruence between the reasoning mind and the structure of reality. So the journey from Newton's clockwork to today's cosmic landscape, it's a story of deepening questions. We moved from admiring the clock's regularity to taking it apart. And when we looked at the individual gears and springs, we found they were machined to tolerances of unimaginable precision. The ancient question, why is the cosmos ordered, it remains, but now it has a numerical, empirical sharpness. We're not just asking why there is law. We're asking why the law has these parameters. This historical arc, it gives the multiverse hypothesis its proper weight. It's not a wild fantasy. It's the latest, most ambitious attempt in a long lineage of thought. An attempt to answer a question that's haunted the scientific imagination for generations. If the numbers aren't chosen, and they aren't necessary, then maybe they're just local. A single setting in a cosmos of infinite possibility. There's this strange alignment between mathematics and the mind. It points to something deeper. The equations that describe reality, they're often beautiful. That's not just a poetic thing. For a lot of physicists, mathematical beauty acts as a guide, a kind of compass. They believe that if a theory is truly fundamental, it should have a certain elegance, a deep symmetry. You see it in Einstein's field equations for general relativity, a concise set of relationships linking the geometry of space-time to the matter and energy within it. It's a breathtakingly simple idea, expressed with this profound mathematical grace. The same holds for the core framework of the Standard Model of particle physics. Its equations are built on symmetry and gauge invariance. They describe how particles interact through forces in a way that feels almost musical, a harmony of fields and particles. That elegance suggests the universe isn't just a haphazard collection of rules. It's more like a unified composition. But then, the constants are the odd notes. The specific measured values the mass of the electron, the strength of gravity. They often look like arbitrary numbers plugged into these otherwise beautiful equations. They break the perfect symmetry. It's like finding a masterpiece painting where all the colors are harmonious, but the exact shade of blue in the sky was chosen by rolling a die. Why these numbers? It creates a tension. On one hand, the underlying mathematical beauty hints at a deeper, unified theory, a theory where all constants are derived, not assumed, where they emerge from a single elegant principle. That's the dream of a final theory, a theory of everything, where the 20 or so free parameters of the Standard Model are all calculated, explained by a grander symmetry. Maybe in string theory or another framework. Then the beauty would be complete. The universe's laws would be not only elegant, but necessary. On the other hand, the fact that these specific values are so exquisitely tuned for complexity might suggest the opposite. That the search for a single beautiful theory explaining our constants is misguided, because maybe the constants aren't fundamental truths to be derived. Maybe they're local environmental conditions. In that view, the mathematical beauty resides in the overarching framework. The laws of quantum fields, the principles of inflation, but the specific outcomes, the constants, are random, scattered across a multiverse. The symmetry and elegance are the canvas. The specific tuned values are just the particular brushstrokes in our corner of the painting. So we're left with a choice. Does the universe's deep mathematical harmony point toward a single, elegant, and necessary set of laws? Or does it point toward a generative engine of immense power, an engine that produces endless variations, only a few of which are beautiful to us because they allow us to exist to appreciate the beauty? Maybe the very fact that we can perceive this elegance is the ultimate clue. We are products of a universe that allowed for minds, and minds seem drawn to symmetry, to pattern, to elegant explanation. Is that a coincidence, or is it a feature of the cosmos itself? A hint that consciousness and the laws that gave it birth are part of the same beautiful story. That tension between elegance and randomness, it leads to a practical question: can we ever find proof? The multiverse has this explanatory power, but it faces a challenge. It might be untestable. If other universes are truly separate, beyond any contact, how could we ever know they exist? That's not just a technical hurdle. It touches the definition of science. A good theory has to make predictions we can check. So are scientists just speculating, or is there a path to evidence? There is a search underway. It looks for subtle fingerprints of a multiverse on our own cosmos. The most promising place to look is the oldest light we can see. The cosmic microwave background radiation. That faint, cold glow from the infancy of the universe. It's a snapshot of the cosmos when it was just 380,000 years old. And etched into that snapshot could be scars, signs of ancient collisions. Think of our universe as one bubble in a frothing sea of eternal inflation. These bubbles expand, and sometimes in that chaotic early foam, two bubbles might have brushed against each other, a collision between two nascent universes. That event would have sent ripples through the fabric of our young cosmos, ripples that left an imprint on that primordial light. Cosmologists are scouring the detailed maps of the cosmic microwave background, looking for unusual patterns. Strange, circular asymmetries in the temperature fluctuations, a kind of cosmic bruise. Finding such a signature would be revolutionary. It would be direct evidence that something outside our bubble once made contact. Another avenue looks at the large-scale structure of the universe, the grand cosmic web of galaxies and voids. The theory of inflation, which gives us the multiverse, also makes specific predictions about this structure. It forecasts a certain statistical distribution for the sizes of galaxy clusters and the vast empty spaces between them. Future sky surveys, like those from the Vera C. Rubin Observatory, will map billions of galaxies with unprecedented precision. They will test these predictions to a razor's edge. If the observed patterns match one specific version of inflationary theory, a version that naturally leads to eternal inflation and a multiverse, it would be a powerful, though indirect, corroboration. It would be like finding the blueprints for a factory that only makes sense if it produces many different products, not just the one we see. The search itself is transformative. It drives the creation of incredible technology, more powerful space telescopes, more sensitive detectors, exascale computing to analyze petabytes of sky data. It pushes the boundaries of data analysis, with scientists developing new algorithms to sift the cosmic noise for the faintest of signals. This pursuit turns a philosophical idea into a dynamic, empirical quest. The mystery of fine-tuning is no longer just a puzzle to ponder. It's a hypothesis to test, a target for observation. While definitive proof remains beyond our current reach, the very act of looking changes the game. It means the multiverse is not a dead-end speculation. It's a living, breathing scientific framework, one that generates questions we can actually try to answer with telescopes and mathematics. The lack of easy evidence doesn't kill the idea. It elevates the challenge. It keeps the mystery vitally alive, a driving force on the frontier of cosmology, reminding us that the greatest questions are those that compel us to look deeper into the fabric of reality itself. That search for fingerprints, it leads to a bigger question. If the universe is so perfectly tuned for life, why does it feel so empty? That's the Fermi paradox. Named for Enrico Fermi, he looked at the number of stars, the probability of planets, and he asked a simple question: where is everybody? The silence is profound. Our galaxy has hundreds of billions of stars, many with planets. The universe is nearly 14 billion years old. That should be enough time. Enough for other civilizations to arise, to spread, to make themselves known. But we hear nothing, we see nothing, we appear to be alone. This cosmic quiet, it stands in contrast to a life-friendly universe. It creates a tension. If the cosmos is so finely tuned for us, why isn't it teeming with others? The multiverse idea offers an answer, a sobering one. In a landscape of infinite universes, the ones that permit life might be incredibly rare. Not one in a million, one in a number so vast it has no name. Our universe could be a singular oasis, an island in an endless ocean of dead, silent realities. In that picture, the reason we don't see others is simple. There aren't any, at least not nearby. We might be the only game in town, the only flicker of consciousness in this entire bubble. The fine-tuning that allowed us also ensured our isolation. It's a lonely thought. It adds a layer of cosmic solitude. We won the ultimate lottery, but the prize is a universe to ourselves. But there's another possibility, one that doesn't require us to be utterly alone. Maybe the same fine-tuning that allows for life also sets up barriers. The constants gave us stars and planets and chemistry, but they also dictate the harsh realities of physics. The speed of light is a universal speed limit. Unbreakable, the distances between stars are immense. It takes light years, centuries, millennia to cross them. For a physical spacecraft, the journey would take far longer. Generations, the energy required to go even a fraction of light speed is astronomical, beyond any technology we can envision. Then there's the fragility of biology. The timescales of cosmic evolution are long, but the window for a technological civilization might be short. A species might arise, look at the stars, and then succumb to its own challenges before it ever learns to reach them. The silence we hear might not be emptiness. It might be the sound of distance and time and limitation. A universe fine-tuned for life might also be fine-tuned to keep that life contained. Separated by gulfs too wide to cross and eras too vast to bridge. This reframes the entire paradox. It's no longer just a question about aliens. It becomes a question about the nature of a fine-tuned reality. Does the precision that crafted us also craft our cage? Are the constants that allowed for stars and planets and minds the same constants that sentence those minds to isolation? We look up at a sky full of stars, each one a potential sun for another world, and we wonder if, out there, another mind is looking back, trapped by the same beautiful, unforgiving laws. The paradox deepens the mystery. It suggests that even in a cosmos built for life, intelligence might be a rare and lonely flame, flickering in a cathedral of space and time so grand that no other flame is close enough to see. That cosmic solitude, it's not just in the equations. These ideas, fine-tuning and the multiverse, they've soaked into our culture. They shape the stories we tell, the fears we have. You see it in movies, characters hopping between worlds, in books where every decision makes a new reality. They're not just clever plots, they're modern myths. A way for us to handle what science is saying, that the universe might be nothing like what people used to believe. For thousands of years, humans saw the cosmos as one creation, often with us right at the center. A story with a start, a point, an ending. Fine-tuning and the multiverse, they cut against that. They suggest we might not be central. Our story might not be the only one. Our universe could be one of countless others, and us being here inside it could just be a fluke, a statistical accident. That's a huge shift. It takes us from a universe with a script to a cosmos that's improvising on an infinite scale. Philosophers and theologians have wrestled with this. Some see the multiverse as a natural answer to the design question. If every possible universe exists, you don't need a designer to explain ours. For others, it just moves the question. Why does the mechanism that makes the multiverse exist at all? This conversation crosses traditions. Western philosophy, Eastern thought, where ideas of infinite cycles go way back. Carl Sagan touched on this tension. He talked about our duty to be kinder to each other, to preserve this pale blue dot, our only home. In a multiverse, those words get heavier. If our universe is a rare, habitable bubble in a vast desert, then what's in it? This planet, life, us, it's not just precious, it's unbelievably rare. Maybe one of a kind. That doesn't shrink the wonder, it magnifies it. The fact that we're even here to think about this against those odds, it feels like the biggest mystery. It changes our place, from one of destined privilege to one of fragile, breathtaking luck. And that shift has an ethical weight. If we're an accident inside an accidental universe, does that mean there's no meaning? Or does it mean making meaning is entirely up to us? A lot of thinkers say it's the latter. In a cosmos without a pre-written purpose, our consciousness becomes the source. Our love, our art, our science, our ethics, these aren't side notes in some grand plan. They might be the only things like them in all of reality. That brings a deep sense of responsibility. For the planet, for each other, for what comes next. It means what we do here matters, not because some higher power is watching, but because in all this vastness, we are the only ones who can make it matter. So the mystery of fine-tuning, it's more than a physics puzzle. It's a mirror. It shows us our own basic human search, to figure out where we stand in existence. Whether we find answers in a single creation or a hidden multitude, the searching itself tells a story. A story about a species on a small rock, looking up at the stars and asking why. This responsibility extends to the tools we're building now. We're searching for meaning, and at the same time, our ability to see is expanding in a breathtaking way. The future of cosmology is about new eyes, not just new ideas. Instruments of staggering sensitivity are coming online. They're designed to probe the deepest layers of cosmic history and the most fundamental laws. Their goal is to gather data so precise it could corner the multiverse hypothesis or dismantle it entirely. First, the James Webb Space Telescope. It's already sent back images of early galaxies. But its most profound work is just beginning. By staring for hundreds of hours into specific patches of sky, it will perform ultra-deep surveys. It will see the very first stars and galaxies as they were forming, just a few 100 million years after the Big Bang. This data is a direct test of our models of cosmic dawn. It will measure the rate of early galaxy formation with exquisite detail. If the numbers match the predictions of our standard inflationary model perfectly, that strengthens the framework. But if it finds something unexpected, galaxies that are too old, too massive, too structured too early, that's an anomaly. An anomaly that could force a revision of inflation itself, or perhaps hint at influences from a broader cosmological environment. It's like examining the first page of a book with a magnifying glass powerful enough to see the texture of the paper, looking for watermarks from another volume. Then on the ground, the Vera C. Rubin Observatory in Chile will begin its legacy survey of space and time in the coming years. This is a different kind of instrument. It won't peer at a tiny spot, but scan the entire southern sky every few nights for a decade. It will catalog billions of galaxies, tracking their positions and shapes. Its primary target is dark energy. By measuring how the large-scale structure of the universe has evolved over billions of years, it will constrain the nature of dark energy with unprecedented precision. Is it truly a constant, or does it vary over time? The answer will refine one of the most critical numbers in the fine-tuning equation. And by mapping the cosmic web in such immense detail, the survey will test the statistical predictions of inflation to a razor's edge. It will look for subtle patterns, correlations, or strange voids in the distribution of galaxies that don't fit the standard story. Such a discovery could be a fingerprint of something far stranger. And then there are the machines that probe the very small. Next-generation particle colliders like the proposed Future Circular Collider aim to reach energies never before achieved in a laboratory. They will smash particles together to recreate conditions a fraction of a second after the Big Bang. Their mission is to search for new particles, new symmetries, any sign of physics beyond our current standard model. This is crucial because the fine-tuning problem is in part a problem of particle physics. The inexplicably small mass of the Higgs boson, the mysterious strengths of the forces, these are puzzles the standard model cannot solve. Finding a new particle or interaction could provide the missing piece. It could reveal a deeper symmetry that makes our constants appear necessary, not arbitrary. Or it could deepen the mystery by revealing an even more precise level of tuning. Together, these observatories and colliders represent a coordinated assault on the unknown. They will provide data of a quality and quantity we've never had. This data will constrain our models of inflation, refining our understanding of how our particular bubble universe came to be. It will measure the fundamental constants with even greater accuracy, searching for any hint that they might change over time or space. And it will hunt for anomalies, statistical quirks in the cosmic microwave background, strange features in the galaxy distribution, unexpected particles in collision debris that cannot be explained by a single, isolated universe. The promise of the next decades is clear. We will either find evidence that strengthens the multiverse hypothesis, making it the most coherent explanation for the world we see, or we will find data that contradicts it, forcing cosmologists toward new, even more revolutionary ideas. Perhaps fine-tuning will be solved by a theory we haven't yet conceived, one that derives all constants from a single, beautiful principle. Or perhaps the mystery will deepen, revealing a cosmos even more bizarre and wonderful than we currently dare to suppose. One thing is certain: the question of why the universe is so perfectly suited for life will not fade away. It will evolve, driven by the light captured by these new eyes on the cosmos. Our grandest story is still being written. The data from these new instruments will change our theories, and it will change us. Finding evidence of a multiverse, that's more than a scientific discovery. It's an existential event. It forces a re-evaluation, the most basic questions: what has value, what has meaning? If our universe is one of countless others, does that make it less special? Or, strangely, more precious? On one hand, it suggests we are not the center, not the intended outcome. Our story is just one of an infinite number being told. That can feel diminishing. Our struggles, our joys, our art, just local noise in a silent cosmic ocean. A perspective that could lead to a kind of nihilism. Why does anything I do matter if somewhere else, every other version of me is doing something different? That's the existential weight. In a cosmos where every possible version of you exists, making every possible choice, the uniqueness of your path dissolves. Your triumphs, your heartbreaks, they're not yours alone. They're shared across a near-infinite ensemble. It can make a life feel like a script, already written in the library of all possibilities. But there's another way to see it. A perspective not of loss, but of responsibility. If our universe is a rare, habitable bubble in a vast desert of dead or sterile realities, then everything within it becomes astronomically valuable. This pale blue dot, with all its life and consciousness, isn't just our home. It might be a singular sanctuary, a flicker of light in an unimaginable expanse of darkness. In that view, every act of kindness, every work of beauty, every effort to understand and preserve becomes not less significant, but infinitely more so. We become the custodians of a miracle. The ethical imperative shifts. It asks us to treat this universe and each other with the utmost care. Because if we are alone in this bubble, or one of a very few, what we do here is the only thing of its kind. Our story is the only one being told from this particular vantage point, with this particular set of laws. That uniqueness, born from cosmic rarity, confers a dignity all its own. The multiverse idea also challenges our notion of self. If every decision branches into a new reality, then the version of you reading this is on a singular thread. The other versions are separate stories. They don't share your memories from this moment forward. They don't feel your feelings. So while the multiverse may contain every possibility, your conscious experience, this one, right now, remains singular. Unrepeatable. It is the only thread you will ever know that can be liberating. It means the weight of every path not taken is lifted. Those other lives are being lived elsewhere. Your path is yours to walk fully, without the ghost of what might have been. It places the emphasis not on the infinite copies, but on the quality of this one specific journey. These questions have no definitive answers. They live in the space between science and philosophy, between data and meaning. The value of asking them isn't about finding a single truth. It's about the reflection itself, deciding for yourself how to live in light of these staggering possibilities. Does a hidden multitude make your life more precious or less significant? The science gives us the framework, but the answer is a choice about what we value, how we connect, what legacy we wish to create within our own, finely tuned corner of reality. The search for a multiverse, then, is also a search for ourselves, a mirror held up to our deepest hopes about our place. There's a lot of confusion around these questions, and it's important to sort that out. One big misunderstanding is that cosmic fine-tuning is proof of a creator. That's not what the evidence says. What it actually is a puzzle. An empirical puzzle. The constants of nature are balanced for life. That's the observation. And then you have different frameworks trying to solve it. Intelligent design, the multiverse, others. The observation itself doesn't pick a solution. It's the starting point. Calling it proof for any one answer shuts down the whole inquiry. It closes off the science, the philosophy. Then there's the multiverse idea. People sometimes think it means anything can happen, like a magical place. But that's not it. Each universe, each bubble, has its own set of physical laws, complete, consistent laws. They might be very different from ours, but they are still laws. They govern cause and effect. If gravity is 10 times stronger in some other universe, you don't fly, you're crushed. The multiverse isn't a free-for-all. It's a structured ensemble, immensely varied, but each reality bound by its own internal logic. That distinction matters. It grounds the idea in rational law, not fantasy. Then there's the criticism that the multiverse is untestable, that it's just metaphysics, but that deserves a closer look. We can't hop between universes, no. But the theories that predict a multiverse, like certain models of inflation, they make testable predictions about our universe. They forecast patterns in the cosmic microwave background. They predict the distribution of galaxies. Upcoming telescopes are hunting for these fingerprints right now. If we find an anomaly, a strange pattern in the ancient light, or a galaxy distribution that only makes sense in a multiverse scenario, that would be indirect evidence. Powerful evidence. So the multiverse isn't a disconnected speculation. It's part of cosmological models being tested every day. Calling it purely untestable ignores how frontier science works. It works by predicting the observable consequences of unseen realms. Clearing this up isn't just academic, it's essential. When misconceptions take root, these ideas get misused. They get turned into pseudoscientific claims, or used to shut down curiosity with oversimplified slogans. Understanding that fine-tuning is a mystery, not an answer, and that the multiverse is a rigorous extension of our best theories, that lets us engage with the cosmos as it is. A place of deep wonder, governed by reason, open to our questioning. The journey isn't about confirming biases, it's about following the evidence, wherever its improbable path may lead. The search for meaning in a multiverse, it shows something. It shows that some of the deepest questions, they can't be answered by physics alone. The fine-tuning problem, it sits at this intersection. Where cosmology meets philosophy, but it's not a collision, it's a collaboration. It's a conversation across disciplines, and it enriches both. Philosophers of science, they help clarify what we're even asking. What makes a good explanation? Is the multiverse a valid scientific idea if we can't observe other universes directly? They examine the logic of probability in an infinite ensemble. How can you say something is probable if every possible outcome happens somewhere? These aren't word games, they're foundational questions. They sharpen the scientific inquiry. They ensure our theories are logically coherent, not just mathematically elegant. And then on the other side, physicists provide the concrete models. The equations of eternal inflation, the mathematical landscape of string theory. They translate philosophical possibilities into testable frameworks. They ask if the multiverse is real, what statistical signatures should it leave on our universe? This back and forth is essential. A philosopher might challenge a physicist's assumption about randomness. A physicist might show a philosopher how quantum mechanics reshapes our very ideas of reality. Together, they refine the questions and the tools used to answer them. Consider the concept of a law of nature. Physics discovers these laws, it measures the constants, but philosophy asks, what are laws? Are they prescriptive rules the universe must obey, or are they just descriptions? Descriptions of the deepest patterns we observe. In a multiverse context, this question transforms. If every possible set of laws exists somewhere, then laws might look more like local bylaws. Rules specific to our cosmic neighborhood, not universal decrees. This interdisciplinary synergy, it breaks down old silos. It acknowledges that a mystery this profound, cosmic fine-tuning, it can't be solved with a single tool set. It requires the rigorous logic of philosophy and the empirical power of physics. Working in tandem, this collaboration extends further to our understanding of existence itself. The question, why is there something rather than nothing? That's a philosophical staple. Now, cosmology offers potential physical scenarios, like quantum fluctuations in an eternal void. That gives concrete shape to that ancient wonder. The dialogue pushes both fields forward. It reminds scientists to question their metaphysical assumptions. And it gives philosophers new, empirical landscapes to explore. The result is a richer pursuit, more nuanced. We're not just cataloging galaxies or debating logic. We're jointly mapping the boundaries of knowledge, learning that some answers about reality, they may be found not only in new data from telescopes, but in new ways of thinking about the data we already have. Look up at the night sky. Those points of light, those suns, they're the final expression of a chain that started with numbers, specific numbers, the strength of gravity. The mass of an electron, the energy of the vacuum, they were set over 13 billion years ago into the fabric of reality. That's what you're seeing. The outcome of a calibration so precise it let those suns ignite and burn for billions of years, long enough for planets to form, and on at least one planet, for atoms to assemble into beings who could look back up and wonder. Your ability to stand there, to feel the air, to ask these questions, is a product of that ancient fine-tuning. It's a personal connection to the grandest scales. The universe wrote rules so specific that, in time, it could produce a mind to read them. That's the heart of it. Whether you see a divine hand in that precision, or the blind luck of a multiverse, or a principle we haven't grasped yet, the fact remains. You are here, contemplating the cosmos that made you. That self-awareness isn't an accident. It's a feature of this particular universe, built into its deepest laws. So what does that imply? It suggests our search for meaning isn't separate from the physics. It's a consequence of it. Our curiosity, our drive to understand our origins, is the universe becoming conscious of itself. Through us, this doesn't dictate a single answer about purpose. It frames the question in a new light. Your wonder, right now, is part of the cosmic story. A story of constants and consequences, stretching from the first instant to this moment. It ties the vast narrative directly to the individual, to your own sense of awe. That feeling, as you gaze upward, is the universe looking back at itself. And in that silent exchange between the stars and the mind that observes them lies a profound mystery. One that belongs as much to you as it does to the physicists and the philosophers. We followed the rules inside atoms all the way out to the idea of an infinite cosmos. And that path shows a universe tuned with incredible precision. Every constant, every balance, the forces that build carbon, the dark energy driving expansion. They all point to one thing: this universe is special. It's a place of complexity in what could have been just silence, a desert of sterile realities. So the multiverse idea comes from that. It's not a fantasy, it's a serious scientific framework. It gives a naturalistic answer to the question of why. If every possible universe exists, then one like ours that permits life isn't a miracle. It's a statistical certainty, but it's still a hypothesis. Compelling, elegant, but not proven. It's at the frontier, challenging us to look deeper. Now, whether that idea of countless hidden worlds fills you with awe or with a sense of solitude, its value is clear. It stretches the imagination. It makes us reconsider everything: the nature of physical law, the meaning of our own existence. It can turn a lonely universe into just one member of an unimaginable family. Or it can turn a finely tuned cosmos into a rare artifact, something precious. Both views have weight, both inspire wonder, and as new telescopes look deeper into the past, and colliders probe the foundations of matter, we're not closing the book on this. We're writing the next chapter. Every refined measurement, every odd piece of data brings us closer. Maybe we'll find the fingerprint of another bubble on our cosmic horizon. Maybe we'll discover a deeper theory that makes our constants necessary. Or maybe the mystery just deepens, leading us to truths we can't yet conceive. This exploration is what science offers. A journey into the unknown, guided by curiosity and evidence.